I'm here, you're here. Let's get started. Good morning, everybody. Welcome to another wonderful morning of Chem 1105 with your host, me, Dr. White. Now, important information. One, tomorrow will be test number 2. And don't forget, I will send out around 10 o'clock the password for whatever version you will be doing for test number 2, and then you'll have until 11:30 to take the test and upload it as a single PDF file to assignment area Blackboard. I've already posted what chapters test number 2 will cover. We've gone through the problem set. I'll be doing something to help you out in a little while for test number 2, as I promised 2 days ago. All right. Now, one of your colleagues asked a good question by email yesterday, and I just forgot to talk about it. In each of the Beyond Labs Z Labs, I will include usually the PDF file that they use. You don't ever have to use it. I just wanted to show you uh, if I were lazy and didn't write my own labs, that's what you'd be doing, working from. And they're some not bad, but mine are better. But you to be the judge of that. But sometimes also you can see in the PDF they also explain how to do the lab or at least operate and manipulate things. But I show you that when we actually do the lab, like I did yesterday. So if you want to look at it, the like 111 PDF file for yesterday's lab, feel free to. If you don't. And that's all you have to do with those. All right. What I'd like to do today is first of all, go through a couple of practice problems that'll help you for tomorrow. Don't tell anybody I'm being nice. They'll ruin my image around here. And next, we'll go back to gases. We'll do a PV equal nRT problem. We'll finish up that chapter today, and we'll move on to the next chapter. Remember, gases will be on test number 3, which is coming up pretty soon, like next week. Wow, it's summer. Things go whoop, real fast. All right. Let's do a little practice. Oh, promise not the right. And let's look at the following. I don't know how many points, 5 or 7 points, depending on my mood. That's the truth. And the first thing I'm going to ask you to do is, first of all, tell me, thumbs up, people. Can you see my whiteboard? Thank you. First of all, why don't you determine what are you trying to find? What are you given? You got 10 seconds. Go. Time's up. I gave you bonus seconds. And the question is, what are you trying to find? And the answer is, how many moles HCl, hydrochloric acid? And we'll learn later on what is an acid. And what are you given? 3.421 grams of HCl. And using your good buddy, your good friend, unit analysis, first of all, this is all I have to start with. If I can multiply it by some conversion factor ratio, what units do I want my answer? And the answer for that answer is moles of HCl. And now it's time to really use your good buddy, your good friend, unit analysis. I love that. And whatever you're trying to get to goes on top of this ratio, and whatever you're going to get rid of goes underneath. And I'll write those in. That wasn't that hard. I hope not. Now, where do I find a relationship between grams of HCl and moles of HCl? Well, you're going to have to hold on because I forgot to open up something. And thumbs up, people. Does everybody see test 2, important information? Thank you. And if you look here, 1 mole of a compound equals the molecular weight of that compound in grams. Again, 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights in that compound. So I know for every 1 mole, I have the molecular weight of that compound in grams. And I also know the molecular weight of the compound is the sum of all atomic weights. And therefore, I can go back here. Well, first of all, I have to figure out the atomic weight of hydrochloric acid, HCl. And how do I do that? That's the sum of all atomic weights. So I need the atomic weight of hydrogen and the atomic weight of chlorine. Everybody see the periodic table on your screen? I hope so. And thank you, Lily. What's the atomic weight? It's the number underneath the chemical symbol on a periodic table. And on test 2 tomorrow, you'll see underneath your name, it will say, please use proper significant figures for all calculated answers. And it will also say, please use 3 significant figures for all atomic weights or masses. I think I say weights. If you don't, I'll take off a point. So hydrogen, the 3 significant figures is 1.01. Chlorine, the 3 significant figures is 35.5. Check it out. I did it right. Yay. And now we have to figure out the molecular weight of HCl. This is my abbreviation for molecular weight. And it's got 1 hydrogen, 1 chlorine, which is equal to 1 times 1.01. I didn't have to do it this way. And 1 times 35.5. That's 1.01, 35.5. Add it up and you get 36.51. Now, it says use proper significant figures for all calculated answers. This is an addition. You get the same number of significant figures to the right of the decimal point as the number that has the fewest significant figures to the right of the decimal point. This has 2, this has 1, therefore, which is a smaller number, 2 or 1? And hope you all took 1. Therefore, you keep the 5. And is this 4 or less? Yes, and drop it. So for every 1 mole equal the molecular weight, in this case of HCl, is 36.5. And now I will look grams of HCl divided by grams of HCl equal 1. Remember, anything divided by itself equals 1 and cancels out. I'm left with moles of HCl. I now can go to my calculator, turn it on, clear it, and do 3.421 divided by 36.5. Hold on one second. And I hit enter, and the calculator gives me this number. And let me clean up one of these numbers. And remember, it says on test 2, please use proper significant figures for all calculated answers. How do you do that for multiplication division? You get the same number of significant figures as the number with the lowest significant figures you're multiplying and dividing. And this has 4 significant figures. I hope you all know how to figure that out. And how many does this have? 3 significant figures. So how many significant figures should our answer have? 3. I'll let you round this number off to 3 significant figures, and then I'll do it. Go. Time's up. Keep the 9, keep the 3, keep the 7. The 1 to round off is, used to round off is 2. Is that 4 or less? Yes. And therefore, everything else you drop, and the correct answer here would be 9.37 times 10 to the minus 2. And if you don't put the units down, I don't care, but I do, moles of HCl. And that's how you do it. Let's do one more. And let me decode this. First of all, you're given a balanced chemical equation, 10 points, so I want to get that one right. And it says if you react 81.6 grams of chlorine gas, Cl2, with an excess of sodium, then how many grams of sodium chloride, table salt, remember, please pass the NaCl, will you make? I'm going to let you try the first thing first. What are you being asked to find? What are you given? Your turn to do that only. Time's up. What are we being asked to find? Grams of sodium chloride. What are we given? Grams of chlorine gas, Cl2. Whenever you see an excess of something, you ignore it. That means you got enough of that to react with anything it could react with. Now, there is no relationship in chemistry where I can go in one step directly from grams of one compound to grams of another. There is none. What you need is 3 steps. And if we look at the important information, which will be included in test number 2, mass calculations. Remember, mass, we're talking about grams for this class, but I've done it for kilograms. I've also done it for pounds. This calculation, the most I ever did it was for, I think it was 160,000 pounds total, which was $160,000 just in the raw chemical costs. So made sure I was doing it. And the first step, you convert whatever you're given in grams to the moles of that compound. Second step, you take whatever you just calculated the moles of A, and you convert to the moles of what you're trying to get to. In this case, it would be sodium chloride. And finally, you convert the moles of whatever you just found, B, what you're trying to get to. Remember, mass is for this class grams of B. So let's do it. So the first step from the important information, it says mass of A to moles of A. What does that mean? Whatever you're given in grams, and that's in this case chlorine, we want to convert to moles of chlorine. So we'll use our good buddy, our good friend, unit analysis. I have grams of chlorine. I want to get to moles of chlorine. I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top of this ratio. Whatever I'm trying to get rid of goes underneath. And this is moles of chlorine. And this is grams of chlorine. And where do we get this ratio? 1 mole equals the molecular weight of a compound in grams. And the molecular weight of chlorine, Cl2, is 2 chlorine. And each chlorine, as we saw earlier, is 35.5. And that's equal to 71.0, in this case, grams. So 1 mole equals 71.0 grams of chlorine. And let's go to my calculator. I'm going to use the spreadsheet for this. All right, now for each of these type of multiple step calculations, I'm going to calculate rounding off at the end and a rounding off like I normally do at each step. So 1.1492 2958, the 3 significant figures would be 1.15. So now I'll write that in. By the way, it pays to show your work on this problem. Because if you make a mistake, I can track it down and then just give you partial credit.
Did you multiply 81.6 by 71.0?
Yeah, but the spreadsheet throws in extra. It takes off when I do the 0.0 in a spreadsheet, it removes it. Okay, this is the right number. That's a good question. But you won't be working, well, I don't know, but use your calculator. It'll be safer for you. All right,
For
now,
some reason, I'm not getting that.
what? You're not getting that number?
No.
All right, let's try it again. Let me do it over here. I get the same number. If you look right over here.
Oh, you're dividing. I was multiplying.
Nope. Yeah.
Okay, I see.
Let's go back, and that's a good question. Do you see where I'm dividing here? That's why. All right, now
Okay.
we've done step one. Now we have to do step two. And step two is moles A to moles B. In this case, we just figured out moles of chlorine, and we want to go to, in this case, moles of the answer, the molecule we want in our answer, and that's sodium chloride. And we use the number we just calculated. Again, this is step two, 1.15 moles of chlorine gas, Cl2. And we want to go to moles of sodium chloride, because that's how you're going to get to the final answer using this three-step. And what do we use? We use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And I'll write them in. And where do I get a relationship between moles of Cl2 and moles of NaCl, sodium chloride? We come up here to the balanced chemical equation. And the coefficient tells us when there's no coefficient, it's really the number one. So what this tells us is 1 mole of chlorine makes 2 moles of sodium chloride. Again, 1 mole of chlorine makes 2 moles of sodium chloride. So I can come down here, for every 1 mole of chlorine, I make 2 moles of sodium chloride. Again, for every 1 mole of chlorine, I make 2 moles of sodium chloride. And that's where you get those numbers. Now, remember, these are exact numbers. Coefficients of a chemical equation are exact numbers. Therefore, if this is 3 significant figures, our answer should be 3 significant figures. And now I'm going to, before I go to my calculator, notice moles of chlorine divided by moles of chlorine cancel out, because anything divided by itself equals 1. Does anybody have any nightmares hearing me and seeing me write this in your mind? I hope not. That'd be scary. But anyways, now I will go back to my calculation and multiply this by 2 and divide it by 1, which is just this. And I now have 2.30 if I'm looking at rounding off at each step. Moles of sodium chloride. Am I done? No. If you come back up here, we have to find grams of sodium chloride. So now it's time for step number 3. And in the instructions, it says moles of B to mass or grams of B. In this case, we're talking about moles, sodium chloride, table salt, 2 moles. Yep. Let's try this again. I have mole on the brain. Ouch. Oh, that was an awful joke. Even for me, that was awful. 2 grams of sodium chloride. And how do we do that? Well, we have moles of sodium chloride right up here, so I'm going to use it here. And now, what am I trying to get to? Grams of sodium chloride. And I'll use my good buddy, my good friend. I don't want to give you siren overdose, but whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. And now I'll write those units in, grams of sodium chloride and moles of sodium chloride. And where do I get that relationship between a mole of a compound and its grams? I look at important information, test number 2, and it says 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. So I need to figure out what's the molecular weight of sodium chloride. It's the sum of sodium and chlorine, all the atomic weights in that compound. So I better get to work. And if you look at the periodic table, I'll give you 5 seconds to figure out for sodium, what's the atomic weight to 3 significant figures. Go. Time's up. Sodium, Na, 22.989. To round that off to 3 significant figures, keep the 2, keep the 2, keep the 9. Use the 8 to round off, that's 5 or higher. So I'll drop that 8 and 9, increase the number in front, 0.9 by 1, that's 1.0. So this would be 23.0 is the correct atomic weight for sodium, which I need to use for sodium chloride, 1 sodium, 1 chlorine, 23.0, 35.5. We did this earlier, finding this. And if I add it up, and keep an eye on me so I don't make mistakes, that's your job. And notice 1 past the decimal, 1. So this is all right. So for every 1 mole, it equals the molecular weight of that compound. In this case, for sodium chloride, is 58.5. Now, before I go ahead and pick up my calculator, or in our case, go to my spreadsheet, I will look, notice moles of sodium chloride will be divided by moles of sodium chloride, and that cancels out because anything divided by itself equals 1, and I'm left with, yay, grams of sodium chloride. And now I can happily go to my calculator, which I will, and take the number we just figured and multiply times 58.5. And now if I round it off, actually this time we'll get a little different. This one will round off to 134 grams. Forget about the zeros. In column H, the 134.5, the three significant figures would be 135. So for my test, either one is correct. Because I'm not going to force you to round off at each step like I do. And let me just clean up something because that's an awful looking 5. I can do better, and I will. Maybe. There you go. So the answer for this problem is 135 or 134. And now I don't want to do that. I hope you found that the two problems I did was helpful for you tomorrow. Make sure you practice your problem set problems before the test, or don't just watch me on the video, because remember the bicycle, if you don't know how to ride a bicycle, first time on a bicycle, boop, you'll fall off. You don't want to fall off on the test, fall off when you're practicing the problems. And one thing you could do is the one I just did, write down the first question from the video, or if you wrote it down, try it yourself. And after you try it yourself, you can look at the video, which will be posted, let's see, sometime this evening. Ooh, that reminds me. Don't forget tonight, because of some personal things I have to attend to, I will be having my office hour from 8 to 9 tonight. That's one time only. The rest of the semester, my office hours will be Monday, Wednesday, 5 to 6. But tonight, it will be 8 to 9. Or if I have to stay a little later, if ever other people need help, I will. Any questions about what I just did? I'll look at the chat. I don't have to do that because it's not that sunny in my. All right, let's get back to gases. Remember, gases will not be on. Dina, not really. I have to move on. I've already done a couple of these. You can go look at the practice problems or come to my office hour tonight if you need more help. But I do have to move on. All right, now let's get back to gases. Gases will be on test 3, not tomorrow's test, which is 2. I like those expensive props I'm using. This is expensive. It's my aunt. And to me, it's priceless. All right, let me do. All right, everybody see PV equal nRT on the screen? Uh-oh, I better get. Thank you, thumbs up, people. All right, we're talking about the ideal gas law, PV equal nRT. P is pressure, it has to be in atmospheres. V is liters, which is a measure of volume. In my test, or in real life, but anyways, for my test and final, I'll always use liters for volume. N is moles, but you'll always get grams. And T is temperature in Kelvin, but any thermometer I've ever seen has been in science, that is, Celsius. So you'll have to know how to convert Celsius to Kelvin. And R is the universal gas law constant. For this class, let's use 0.0821 atmospheres liters mole K. R is a calculated value, therefore this is 3 significant figures. It's not an exact number. Remember that. All right, let's do a PV equal nRT problem. Or, you know something, I'm gonna move on. We're gonna, after the break, I'm gonna come back and do the PV equal nRT problem, because if I look at the clock, it's gonna take more. So we're gonna move on, and I'll come back after the break later on. All right. Uh, one sec. All right. I said I'll come back after the break because it's going to take longer, but this is a short one. Let's talk about Dalton's law of partial pressures. And it's time for me to be subtle. And you should know it. Now, I will never ask for you to write down what is Dalton's law of partial pressures. And the law is the total pressure exerted by a mixture, and this should be of gases, of a mixture is the sum of the partial pressures of the individual gases. Now, what's a partial pressure? Good question. Oh, look, it's defined. I'll never ask you what is a partial pressure, but you should understand the concept. And a partial pressure is the pressure that a gas in a mixture would exert if it were alone under the same conditions. So if you have a mixture of gases, the partial pressure of each gas is the pressure that if we're alone, what it would be. And therefore, what really you should know, and this will be given to you, Dalton's law of partial pressure, the total pressure of a mixture of gases is the sum of the partial pressures. And what this N means is if you had 10, you do 4 plus 5 plus 6, 7, 8, 9, 10. And if you only have 2, it would be P1 plus P2, where P sub number is the partial pressure. 2 days later, I'll be done. All right, 1 second. All right, if you have a mixture of argon with a partial pressure of 421 torr and nitrogen gas, N2, with a partial pressure of 111 torr, then what is the total pressure of this mixture? So what do we do? What are we being asked to find? The total pressure, which I will abbreviate this way. What are we given? The partial pressure of argon is this, and I'll abbreviate it like this. And what else are we given? The partial pressure of nitrogen, which I'll abbreviate like this. And how do you do this? You use Dalton's law of partial pressure. P total equals the sum of the partial pressures of the gases in the mixture. So that would be P argon, partial pressure argon, plus partial pressure of nitrogen. In this case, that's 421 torr plus 111 torr. And I'm going to see if I can do this in my head. And the answer would be, add them together, 532. And that's Dalton's law of partial pressures. And this is an important law because if you think about it, many of the things in our daily life are mixtures. Right now, you're breathing a mixture of nitrogen and oxygen. And you can find out what's the total pressure and what's the partial pressures for each of the gases. Give me a second. Oh, that's not what I want. All right. Do we got time for another one? You know something? I bet you know a lot of some things. You know something. Yeah. But anyways, let's take a break now instead of me rushing and everything. Come back at 9:50, 5 minutes from now. I'm going to go stretch, and this gives you time to recharge your brain or whatever you do in that 5 minutes. I'll see you in 5 minutes. Let's get going. One of my hobbies is model railroading, and just I love trains. I think I might have told you, maybe I didn't. One of my fondest memories that I've done a couple of times uh, in Europe, they have much better train system than the United States, much better. Even though the United States has improved, it's not at the same level. And when I'd be in Amsterdam, uh, two companies I worked for over 20, 15-year or longer period, I'd spend a lot of time in the Netherlands. And right before I flew back to Chicagoland, where I live and I still live, I would always have a way of figuring out. I'd arrive in Amsterdam Friday late afternoon, and I'd fly out Sunday morning. So I had a couple of days to, how should I say, have fun in Amsterdam. And one thing I like to do is like Saturday afternoons, I would get a beer. You could walk around with a beer in your hand in Amsterdam, at least back then. I don't know about now. And I'd go to the Amsterdam Centraal, the central train station, which was right a couple blocks from where my hotel was, one of the better ones in Amsterdam. And I'd spend a couple hours just watching the trains come in and out. It was fun. I'm a train nut. But anyways, let's do another Dalton's Law uh, problem, and then we'll do a PV equal nRT problem. And remember, Dalton's Law is the total pressure of a mixture gas is the sum of the partial pressures. So let me give you one. I'm slightly rewriting it. I'm having a bad writing day. Sorry. All right, let me decode this. A mixture has neon gas with a partial pressure of 222 torr and helium with a partial pressure of 333 torr. then what is the total pressure of this mixture? Your turn, go. And when you're done, give me a thumbs up. All right, I think everybody's done. Well, let me do it the scientific way. I don't know. Wrong question, sports fans. Let's end polling. Let's do the right class. Once in a while, I had problems with my microphone when I started out. Right question. All right, I think most of you are done, so I'm going to get to work. I'll give you another 22.7 seconds. Go. I think time's up. So the question is, first of all, what are we being asked to find? And the answer is to that question, we're trying to define what's the total pressure, which I'll write this way. What are we given? We're given, let me move this out of the way. We're given the partial pressure of neon. And we're given the partial pressure of helium. And whenever you hear this or see the word partial pressure, you should think of Dalton's law of partial pressures, which is P total is the sum of all partial pressures. In this case, that would be partial pressure of neon plus the partial pressure of helium. And in this case, that's 222 torr. And the other one is 333 torr. If I add those up together, I'll get 555 torr. And that's how you do it. All right, now, as promised, let's go back and look at PV equal nRT. And remember, for PV equal nRT, pressure has to be in atmospheres. This is for test 3, remember. Volume, I'll always give you in liters. By the way, I've never seen a gauge in my life that measures atmospheres. It's always something like either in Europe or in certain labs, it would be torr. Also in the United States and plants, a lot of times it's inch pounds per inches of mercury. But anyways, which I can convert, but I didn't ask you to convert to atmospheres. However, N is moles. I've never seen a balance that measures moles, but I have seen many that measure grams and temperatures in Kelvin. But all the thermometers I've seen are in Celsius. And you've learned how to convert that. And this will be given to you in test number 3, important information, which you're not taking tomorrow, but you'll be taking soon. Thanks, Dr. White. I needed to hear that. You're welcome. All right, let's do a practice problem with PV equal nRT. And I'm going to write it out, so please be patient. All right, let me read this to you. A car tire contains 11.5 grams of nitrogen gas, N2, at 25.1 degrees C and 758 torr. What is the volume of the nitrogen in that tire? And right over here or anywhere else you want to do, I'm going to give you about 30 seconds. You figure out what are you trying to find and what are you given. All right, let's take a look at this. What are you being asked to find? The volume of the nitrogen. So you're being asked to find volume. What are you given? There's 11.5 grams of nitrogen. You have a temperature of 25.1 degrees C, and you have a pressure of 758 torr. How do I know that's the pressure? Because torr, millimeters of mercury, and atmospheres are all units of pressure. Now, as soon as you see this, nothing is changing. None of the variables are changing. We're being asked to find something, and this is a little hint too, 15 points, but you need excuse me, you need to use the ideal gas law, PV equals nRT. And in important information, R is given to you, plus the units, which are important because they remind you what units the different values of PV and NT should be. So what are we trying to find? V. I'm going to let you try first. I'll give you a minute without putting any numbers. Just with this equation, solve for V. Your turn. And once you just solve for V, don't put any numbers in, give me a thumbs up. And those who finish early, please be patient. I try and give all students, all of my customers, yep, you're my customers, time to finish. Everybody finish. I think I'm going to name this class the I don't want to use the thumbs up button emoji class, or just no thumbs up class. Nah, I won't. All right. What are we trying to find? Volume. We're using PV equal nRT. In order to solve for volume, we need it alone on one side. Oh, it's not. There's the pressure. How do we get rid of something when you're multiplying? Divide by it. Anything divided by itself equals the number 1. It's gone. Well, whatever I do to one side, I have to do to the other. And anything divided by itself is 1 times V is V. So I now know V equals N moles, R the universal gas law constant, T temperature but in Kelvin, and divided by P pressure in atmospheres. But oh no, we don't have that. So now we've got a lot of work to do. And that's why this is 15 points, because it's a lot of work. Let's do the first thing. Let's find N. N is moles. And whenever you see moles, look for weight. And I have 11.5 grams of nitrogen. And what do I want to get to? Moles of nitrogen. And I'll use my good buddy, my good friend, because if there's a ratio that I convert grams to moles, what do? Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. Whoa, wrong color. Right color. And where do I get these numbers? Remember, 1 mole of a compound equals the molecular weight. So I need 1 mole of nitrogen gas, N2, and I have to calculate that. And how do I do that? Well, I look at my periodic table. Let's do that. And what's the atomic weight of nitrogen to 3 significant figures? Time's up. Here's nitrogen 14.007. Keep the 1, keep the 4, keep the first 0. Use the second 0 to round off. Is that 4 or yes? Of course it is. So I'm going to drop that and a 7. And that's 14.0 for the atomic weight of nitrogen, the element. But I'm doing nitrogen gas, which the molecular weight is 2 nitrogen equal 2 times 14.0 equals 28.0. So here I'll put 28.0. And now, first of all, I'm going to write this down or I'll forget it, because when I go from one screen to another, I might forget it. I'm going to go to my calculator. First of all, I'm going to clean this up. And I'm going to take and do that. Now, I'm going to round this off to 3 significant figures. Forget about the zeros. I have this formatted, so I'll do that. And now I know that, let me go back and check this out. The number of moles of nitrogen is 0.411. Well, that's the first thing. So I've got this. I'm given right here, temperature. Now, common mistake on this type of problem, student just uses this in PV equal nRT, and you'll get the wrong answer. And I'll mark it wrong because it has to be in Kelvin. How do you know? Look at R. R has Kelvin in its units. So I have to go to temperature in Kelvin. And remember, and this will be given to you in important information test number 3. Kelvin equals degrees C plus 273. In our case, it was 25.1 plus 273, and that would be 298.1 Kelvin. Remember, when you're adding, you get the same number of significant figures to the right of the decimal as the number you're adding that has the fewest significant figures to the right of the decimal. But this is an exact number. So I have 1 past the decimal. This is the only number I'll use to determine that. And I have 1 past the decimal. Tricky, aren't I? Well, actually, that's just the way you do it. Am I done? No, I need pressure. And pressure, if we look at R, the units for pressure in that is atmospheres. So pressure has to be in atmospheres. And now I'm going to say, well, I have 758 torr. And if I could multiply it by some ratio, what units do I want? Atmospheres. And once again, I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. And where do I get? Oh, first of all, I'll write these in. And where do I get this number? In test number 3, important information, I used to make students memorize this. 760 millimeters of mercury equals 760 torr equal 1 atmosphere. So for every 1 atmosphere, there's 760 torr. Now, both of these are part of a definition, so these are exact numbers. And therefore, this is 3 significant figures. My answer should be 3 significant figures. And now I'll go to my calculator. If I round it off to 3 significant figures, I get 0.997. And let me go back and look. Right now, I'm doing over there. And now I have the key variables in my V equals nRT divided by P. So let me write it over here again. What's N? Right here. 0.411 moles of nitrogen. What's R? This number right here, 0. I'm going to have to go lower because I'm going to run into this. And guess what? This happens in a whiteboard too in a classroom. I'm going to put it here. N was 0.411 moles nitrogen. R is 0.0821 atmospheres, liters per mole Kelvin. And then the temperature was 298.1 Kelvin. And this was divided by the pressure right here, which I didn't write down. Let's go back and look at it. I think I know what it is, but I don't want to be wrong. 0.997. Atmospheres, if I can spell it. Now, before I pick up my calculator, I'm going to check the units. This is another form of unit analysis. Now, I'm going to ignore this in the bottom and just pretend we have this top part alone. And notice moles divided by moles. That cancels out. Kelvin divided by Kelvin. That cancels out. And now if I look at the top, all I have is atmospheres liter, and that's divided by atmosphere, so that cancels out. And what's left standing? Liters, which is a measure of volume, so I did this right so far. And now I'm going to go to my calculator. Oh, common mistake students make when they're doing this calculation, when they put it in their calculator for R, they put in 0.821, not 0.0821. So be careful. Now, let's do the top part. It's easier on a spreadsheet to do this times R times the temperature, and then take this and divide it by the pressure. And the number I get is 10.07. And if I do it this way, I get that number. Now, both of these should be 3 significant figures. And if I round off in column G, let me do this to make it so you know red is our answer. And I round that off to 10.1. And if I round this off to 3 significant figures, I get 10.1. Oops, 1. So the answer is 10.1 liters of nitrogen in a car tire that contained originally 11.5 grams at these conditions, which is about right now what it is outside. And that's how you do it. Now, before I'm going to go through this again to show you how I did it, because this is important. But if you go to Google, and by the way, I'm old fashioned, can't you tell? Ooh, that wasn't good. But anyways, I never use Google as a verb. But if you go to Google and put in the volume of a car tire, Dr. White did when he's setting up this problem, it's about 10 liters. Now, a number of years ago, car dealerships started offering in other places to put in pure nitrogen gas when you fill up your tires. And I think they put the little green cap on there to let you know, or other people know it's nitrogen in there. Because normally before then, and I still now, a lot of people, including me, use air. And I'm not sure the exact rationale for using nitrogen in your tires, but I could guess one, it's a little pure in the sense that there's should be less moisture in there. But if you ever use a compressor, when it's running, take your gauge, which should have a little knob on it or a little post on it, push it in there and let some of the air out before you fill your tires, and you'll see water come out. That happens in a compressor. I always do that so you won't get water in your tires. The other thing they claim is, or could be they claim, is oxygen will attack rubber. And I see Rain saying staying at the same right PSI, and I don't buy that one. That's my personal opinion. I think really the problem is they're trying to convince people it makes the tire last longer because it won't be affected by the oxygen under high pressure. But at the same time, in the atmosphere around it, your rubber tire is being affected by oxygen. And guess what? All the years since they've been doing nitrogen, my sister does it, and I don't, because thank you, Rain. But anyways, I don't, and my tires usually I can get about 50 to 70,000 miles before I got to get new ones before they get unsafe, which is pretty good for car tires. I have a Ford Explorer, but the other thing I do is religiously, I mean it religiously, once a month, I check my car tires and I make sure they're at the proper pressure. For my tires, that's 35 PSI, pounds per square inch. All right, let's go through that again, the problem, because I think this is important for you to know how to do. I see and thank you, Rain. All right, what was the question? 15 points. A car tire contains 15.5 grams of nitrogen at 25.1 degrees C, 758 torr. And you're being asked what is the volume of the nitrogen in the tire. So if you look at this problem, and I haven't used this word, so everybody take a deep breath, let it out. Don't turn blue on me, please. Take a deep breath, let it out. Hopefully you're nice and relaxed now. These are, stay relaxed, word problems. If you have word problems in math, you can use what I'm teaching you to do that. In fact, when I've taught this method in chemistry, general chemistry, both 1105 and 1211, students have come to me and said, you know, I wish I'd learned this before I took math, because then I could do better on the word problems. And the answer is yes. And the problem solving process is the same. Find out what are you being asked to find. In this case, volume of the nitrogen in the tire. What are you given? The weight of the nitrogen. You're also given the temperature and the pressure. And important information I'll give you are the universal gas law constant, 0.0821. As soon as you see a problem dealing with gases and nothing is changing, and you're given more than one measurement, like volume, weight, temperature, and pressure, when you're given that, you know it's PV equal nRT, the ideal gas law. And in this case, how do you solve for something? We're solving for V. We want it alone on one side. How do you do that? Well, to get rid of the P, since it's multiplied by V, divide by P. Anything divided by itself is the number one. Whatever you do to one side, you have to do to the other. I did. And the P over P times V, 1 times V is V, and the other side is nRT divided by P, the pressure. Now, common mistake, students just put these numbers in. No, you have to have the values in the ideal gas law with the right units. And how can you tell what the right units are? Well, you're going to be given R. And R, the units right here, a reminder. Atmospheres is pressure, liters is volume, moles are moles, which you can convert from grams to moles. You better know how to do that tomorrow, because I went through that earlier today. And the temperature is in Kelvin, but you're given it in Celsius. So now we have to do some conversions. And now when I go grams of nitrogen, I want to get to moles of nitrogen. I use unit analysis. Whatever you're trying to get to goes on top. Whatever you're trying to get rid of goes underneath. And remember, 1 mole of a compound equals its molecular weight. In grams, and the molecular weight is the sum of all atomic weights. So for nitrogen gas, N2, I need 2 nitrogens, 2 times the atomic weight of nitrogen. Remember, this 2 is an exact number, is 28.0. I put it in there. Remember, when you're multiplying or dividing, you get the same number of significant figures in your answer as the number you're multiplying and dividing as the smallest significant figures. Remember the 1 here, an exact number. And this is how I got, let me clean this up. Four point 0.411 moles of nitrogen. Next, I want my temperature in Kelvin, and you'll be given this formula like in test 1. For test 3, important information, you'll need that, so I'm going to give it to you. I've cut down to memorization in this course. Kelvin equals degrees C plus 273. You're given 25 298.1 degrees C plus 273. So the answer is 298.1. And finally, we have pressure. And pressure, and this is the biggest mistake. I get your attention. The biggest mistake on these type of problems that I see is totally awful humor Wednesday. Sorry, but anyways, what I see on a test when I'm grading those is people just put in the pressure in torr or millimeters of mercury. No, the pressure in PV equal nRT is always in atmospheres. So don't make that mistake. You'll get it wrong. And how can you tell? Look over here. One of the units in R is atmosphere, which tells you the pressure for this right here has to be in atmosphere. So we're given torr. How do we convert to atmospheres? This is what we start with. This is what we're trying to get to. Use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. Where do I get these two numbers? From the relationship 760 torr equal 1 atmosphere. 1 atmosphere, 760 torr. Both of those are exact numbers. So this was 3 significant figures, our answer is, and I put it in. We now, because we took the time to do this, figure out what V is. And now we can just drop in the numbers and do the math and check your units first. And that's how you do it. Any questions about that? And now you know why it's 15 points. That's a lot of work. But it's an important aspect of gases, one of the most important. And before I leave PV equal nRT, and we were talking about car tires, remember PV equal nRT is the equation that tells you in the winter, you should check your car tires. Why? Because the temperature goes down in your tire, the volume, the moles, and R, which is universal constant, gas law constant, stays constant for PV equal to nRT. If these are constant, if the temperature goes down, then the only thing that can change on the left is the pressure going down. And I told you a story about how when it was super cold and I came out to start my car and drive it around on a Saturday morning, because it had been out all night in super, super cold weather, I saw if my tires looked flat. No, it was PV equal nRT. And that's because the gas inside was so cold, the pressure reduced. And PV equal nRT tells you, check your tires in the winter. And in the summer, PV equals nRT also tells you, keep an eye on your tires. In the summer, the temperature goes ways up. And let me write it over here. If the temperature goes way up, R, N, and V never change in your tire unless you got a flat or a blowout, which I hope you don't. But if you don't, they don't change. So the only thing on this side can change is the pressure, and that goes up. So keep an eye on your tires when it gets real hot. I'm going to be quiet. We've been lucky. Ooh. Well, I'm going to be quiet. We've been lucky this summer. I don't want that to come out. Uh, Sad to hear about what's happening to people on the West Coast with the temperature this summer. Global warming? Nah, it's not real. Yeah, right. All right. Any questions on PV equal nRT? Well, in that case, you know what time it is? It's new chapter time. Oh, this is a double whistle time. New chapter time. And the new chapter deals with solutions. If you think about it, we've talked about gases. What are the three states of matter? Solid, liquid, and gas. We've talked about gases. Let's talk about solutions, which in our life is mainly liquids, but doesn't have to be. And I looked at the syllabus, and I didn't have this down here that will be covering it, even though I do have, it'll be on the test number 3, but this is what we'll be talking about. And let me just clean up something on my. All right, thumbs up, people. Help me out. Do you see chapter 5, part 2, solutions on your screen? Thank you. All right, this chapter is about solutions. What's a solution? Good question. Thank you. Well, you should know there's different ways of defining this. One way is it's a mixture in which one substance is uniformly dispersed in another. Another way of saying what is a solution, it's a homogeneous combination of two or more substances, and this is important, in which each substance retains its own chemical identity. When you mix two things together to make a solution, neither compound or material changes. It does not undergo a chemical reaction, and that's a solution. So solution is when you mix two things together, it's the same throughout, which is what we mean by the fancy word homogeneous. And when you mix two things together, they don't change their chemical identity. They each stay that way. And before we leave the slide, let's think about solutions in our daily life. Can anybody think of a solution? The air I'm breathing is a solution. It's a mixture mainly of nitrogen and oxygen. I bet you didn't think about it. You're walking around in a solution. Plus, it also has a few other minor things like water. We call that water vapor or water in the gas phase, or for the weather, we call that humidity. And air is a mixture of oxygen, nitrogen mainly, but it also has water in it sometimes. And my unfavorite, really, I hate with a passion, is hot days in the summer when it's really humid. Because then you're going to see, I've got my winter beard on and it's not comfortable. Also, this is my spring and summer and fall beard, but still, it's hot and I don't like it at all. No. So that's one solution. What would be another solution? Hold on. My tea, it's a mixture of different things. It's a solution. Also, which I'm not doing, but if I took water and poured in some salt and mixed it up, it would be the same throughout. You couldn't see differences. That would be a solution. Oh, this is getting freaky. It's all around us. I could do the same thing if I put sugar in there. I'd rather drink sugar and water than salt and water. No, I don't want that. But what's another one? How about the gasoline you buy? That's a very, very complex solution. Gasoline is made up of many different components that used to run a car or an SUV, like in my case, which you can call globally a car. So solutions are all around us. If you want to have some fun, go look either in your bathroom, like your mouthwash, that's a solution, or go into your kitchen and look at things. If you have, what would be a good example? Milk is not a solution. I'll teach you about that later. But if you open your refrigerator, you might find some solutions, like if you have a bottle of pop in there. Now, if you're really fancy, if you have a bottle of wine or a bottle of champagne, those are all solutions. So solutions like chemistry is all around us, literally the air. That was a good joke and lead in. So we have solutions. Now, there's an important concept about solutions, and that is when you have a solution, you have two things. Solutions contain a solvent and a solute. All right, it's Subtle Wednesday. Aren't you glad Dr. White can be subtle? And let's look at this. You should know that a solvent of the solution is the component of that solution present in the greatest amount. The solvent of a solution is the component present in the greatest amount. And the solute of a solution is the other component or components that are present in a small amount or smaller amount relative to the solvent. So in a solution, you can have only one. Hold on one second. I clicked the top of my mouse. Sorry about that. You can only have one solvent, but you can have many solutes. Remember that, one solvent, many solutes. And that's the solution, because the solution is a mixture of two or more components. One will always be the solvent, and the other will be solute or solutes. If I look at the clock, I think this is a good time to take a break. We're a little out of phase than normal. Actually not for now. Let's take a break and come back at 10:50. And with that, I'll see you in 5 and come back at 10:50. Time to get going again. All right, we're talking about solutions. Remember, solutions are a homogeneous mixture of two components that neither one react with each other when you put them together. Now, homogeneous means the same throughout. Now, I'm not going to do it. Notice I got a new refill. But anyways, what if I were to put sand in here and mix it up? Would it be a solution or not? Time's up, and the answer is not, because the sand would float all the way to the bottom. It's not soluble in water, and it wouldn't be homogeneous. So a mixture of sand and water is not a true solution by definition. It'd just be a heterogeneous mixture, but it wouldn't be a solution. But if I were to put, say if I squeezed or put lemon juice in here and some sugar too, and then I have some lemonade. Lemonade, if you filter it and get the pulp out, now I'm being real picky. But anyways, it would be a solution. See all the solutions we have in our daily life? They're everywhere. Now, again, we're talking about a solution contains one solvent. That's the component present in the greatest amount. But it can have many solutes, one or more. And that's the other components, which are always present in a smaller amount relative to the solvent. And Dina, the answer is yes, it is, but that's another aspect which we'll get into later in the semester. I just had a private message from someone, but I responded. All right, let's take a look at solvent and solute. Everybody see my whiteboard now? And the question is, if a solution contains 35 grams of sodium chloride, table salt, NaCl, and 125 grams of water, then what is the solvent and what is the solute of this solution? Well, how do you do that? The solvent is the component present in the greatest amount. And I hope you all agree 125 is greater than 35. So the solvent is water. And all the other components, in this case, sodium chloride, is the solute. And that's an important concept to understand. Oh, let's do this again. I'm gonna let you try one. All right, let me decode this for you. If a solution contains 47.6 grams of HBr, hydrobromic acid, and 75.3 grams of water, H2O, then what is the solvent and solute of this solution? Your turn. And when you're done, give me a thumbs up. Or better yet, I'm going to do a polling on this one. All right, I think everybody wants to press the I'm done button or yes button has done it. So let's get going. And the question is, if a solution contains 47.6 grams of HBr and 75.3 grams of water, then what is the solvent and what is the solute of the solution? The solvent is the component of the solution present in the greatest amount. And which is greater, 47.6 or 75.3? And time's up. Hopefully you pick 75.3, so the solvent is water. And the solute is all the other components, in this case, only one, HBr. Oh, let's do one more. All right, let me decode this. A solution contains 125 grams of ethanol. That's the chemical found in alcohol. Let's say alcohol found in alcohol, things like vodka, Canadian Club, some of Dr. White's favorites. And it contains 25 grams of sugar and 75 grams of water. That'd be a sweet drink. But anyways, what is or are the solvent or solvents or the solute or solutes of this solution? Your turn. I think everybody's probably done. So I can close this. And if we look at this, the first thing is, what is the solvent of this solution? Remember, there's only one solvent, and the solvent is the component present in the greatest amount. So which is the largest number, 125, 25, or 75? Hopefully all pick 125. So the solvent for this solution is ethanol. What are the solute or solutes? There would be two, and that would be sugar and water. So remember, the solvent is the component present in the solution, the greatest amount, and all other components are called the solutes, and that's how you do it. Now, interesting thing, in many things in our daily life today, water, mainly water, is the solvent, but not always. And when you get into industrial organic chemistry, which I've worked in, and even when I worked in a research lab for my PhD thesis, we used other chemicals as solvents. Water wasn't. Well, a lot of the reactions I did where you made mixtures, and after it reacted, you had a mixture, there was no water present. So water does not have to be the solvent, but for many things in our daily life, it is. Just look in a bottle of pop. The main component of pop is water. Remember, Dr. White's from Chicagoland, the stuff in a can or a bottle that's carbonated with CO2, carbon dioxide, and has no alcohol in it, we don't call soda, we call pop. Now, if you think about a can of pop or a bottle, by the way, did I tell you? Yeah, do I have time? I do. Time for a non-chemical thing from Dr. White. Everybody see on their screen right now? Let me check. Yep, it's on there. All right, this is called Werner's, and I can find it mainly at Jewel. Sometimes other places have it. I get the regular, I don't buy. I used to buy the dietetic until I found out the chemicals and sweeteners, artificial sweeteners, are quite bad for you. In fact, I'm going to talk about that in a second. But anyways, Werner's is a very, very spicy, highly carbonated, delicious ginger ale. I'm not a big ginger ale fan until I found out about Werner's. And then for now, many decades, I'm hooked on that. My other favorite is Dr. Pepper. Time for a life story that has nothing to do with, well, not really solutions, but I thought I'd pass it along because I just thought of artificial sweeteners. A couple of years ago, I made some Dr. White's a cook for myself, pretty good one, I think. Well, my friends think so. Anyways, oh, if I did, I don't think I told you this. If somebody says they're a good organic chemist, they're a good cook. They tell you they're a good organic chemist and a bad cook, they're lying to you, because every good organic chemist I've ever met also knows how to cook. It's part of working in the lab. Is similar to working in the kitchen, except in the lab, you don't eat it. But anyways, I'd made my own kimchi and I did something wrong and it gave me food poisoning. Yep. And it was not pleasant. I was at the doctor getting some stuff to knock it out of my system and help me out. And I was telling him, yeah, I read an article, this was a couple of years ago, in the New York Times, and these two gastroenterologists, stomach doctors, whatever that is, I forgot the name, were both overweight, were trying to lose weight. And they were looking at the fact that they were having trouble, but they were consuming products with artificial sweeteners. So they did a study, and the was the probiotics, the flora in your stomach, the microbes that help digest your food, like Pac-Man. Ooh, how do you like that one? Anyways, they measured what happened to the probiotics, that flora in your after you ate uh, anything with an artificial sweetener. And they also had some of their friends uh, submit samples, and I'll let you think about what kind of samples they measured. A stinky type, but you know now. And they found out all the microbes, the flora, your probiotics, when you consume something with an artificial sweetener like in pop, it killed most of them. And within a day or so, they'd come back. But when that happened, that would make you more hungry, which is just the opposite of what you're trying to do. Lose weight is eating something with lower calories, so you lose it. But that stuff affects you in a negative way. So I asked my doctor about that because I was having problems with my stomach, food poisoning. And he said, should I give up? You know, because back then, Dr. White is not a skinny person, never has been. I was using a lot of pop and other things, tea with my artificial sweetener in there. And they said any kind, doesn't matter whether it's Equal or Splenda, any of those will kill everything in there. Not make you sick, but anyways, he said, you know, my stomach doesn't do well on gum or things that have artificial sweetener. So he told me, yeah, that might be a good thing. So after many years of using artificial sweeteners, I gave them up. And I started drinking. Well, I brought my cup of tea down. I've cut back on caffeine a number of years ago. I used to drink about, especially when I worked in the chemical industry, I'd have maybe 8, 10 cups of tea. Each cup is 2 cups liquid. That's a lot of caffeine. I've cut back. So, but anyways, I put sugar in my tea. I've donated to the local food bank the couple cases of artificial flavored or sweetened pop. I had Verner's and Dr. Pepper's, my other go-to stuff. And I went and got all that, and I started using sugar in my tea. I thought, well, yeah, better be careful. I'm going to gain weight. And I did, and I started losing weight, some, not a lot. And since then, I've stayed totally away from artificial sweeteners because that article, I believe, was right. Now, that's my personal opinion. I think about it on your own, but I thought I'd talk about that. All right. And the pop, where I was getting to, has a complex mixture. When you pour it in your glass, you know how the little bubbles come out? Well, there's not only water in there and the flavoring and sugar, there's also carbon dioxide dissolved in the water, the liquid, and pop is a very complex mixture. It's a solution, really. Now, when we talk about solutions, I've already talked about the fact solutions can be mixtures of gases. Solutions can be liquid, like CO2 and pop. I did the salt water, did the sugar. And you can also have solid solutions. I don't work in that, but an example would be brass is technically and steel a solution. And the old dental fillings with mercury amalgam, which they don't use anymore, because mercury is not good for your health, a lot of people feel, are all mixtures or solutions. Now, water is a solvent, and we call it a polar solvent due to polar bonds. You should know water forms hydrogen bonds. And I might have talked about it earlier, but let's talk about water now. Water. Now, I mentioned a long time ago electronegativity. When I did mention I turned the switch, will that be actually on a test in the off position? Well, let's go back and look at electronegativity. And here, everybody see the periodic table? Thumbs up, people. Help me out. Thank you. When you go from the left to the right, atoms are more electronegative. That means when they're sharing electrons in a covalent bond, they're not equally sharing it. And hydrogen, oxygen, notice oxygen's all the way over here, while hydrogen's all the way on the left, the one of the least electronegative, where oxygen's pretty strong electronegative. So what does that mean? For now, I'll use a line where there are 2 electrons here, but oxygen is holding the 2 electrons a little closer to itself. So this is little delta, means there's a slight negative charge. By the way, oh, I'm not in red, so let me erase this. All right. Time out while I close some things here. I gotta, this happens every once in a while. All right, we're back. Hopefully things are working now. And they are. All right, if we look here, first of all, and make sure you can see it. All right, everybody, can you see the, thank you. All right, so what that means is there's a slight negative charge, and this means slight, tiny delta, tiny difference. And on hydrogen, there's a slight positive charge, both of these. And as in life, opposites attract. And this is called a Coulombic attraction. And oxygen will be attracted to the hydrogen in another molecule of water. And the slight attraction we call a hydrogen bond. And you should know this. And water can hydrogen bond to other molecules, which helps make it soluble to form solutions. And another thing you should know about hydrogen bonding is that water has a much higher boiling point than other molecules with the same molecular weight. Usually molecules with similar molecular weights have similar boiling points, but water is much, much higher. And you should know, why is the boiling point of water higher? Oh, let me not abbreviate. And you should really know this. The boiling point of water is higher or high because of hydrogen bonding. That's this tiny little interaction between the slightly negative oxygen and the slightly positive, there's a plus charge here, hydrogen of different water molecules. And that makes a difference. And people ask, oh, you're getting bent out of shape. Why is that a difference? Well, think about it. How would life evolve on our planet if this stuff at right now, the temperature of my house, my room here, yours, was a gas, not a liquid? Well, think about it. First of all, I'm gonna have a drink. Oh, that's good stuff. City water is really good. But anyways, your blood has water in it. And at our temperature, your body temperature, which is higher than room temperature, if water didn't hydrogen bond, your blood wouldn't be a liquid at this temperature, it'd be a gas. Think about how would we look if we had not liquid blood, but gas blood? A heck of a lot different than we are how we evolved now. And so hydrogen bonding, and I'll talk about other things, plays a major role in our daily life. All you have to do is look at the oceans or open up the tap water, your kitchen sink, bathroom sink, or whatever. And the stuff that comes out of it, hopefully it's water, is a liquid, not a gas. Boy, this chemistry is starting to get freaky scary. Not really. All right, let's move on. And other polar solvents, I'll talk about it, can hydrogen bond and make soluble homogeneous solutions. Ethanol is one, isopropanol is another. Uh, what are these? I'll teach more about it later in the semester, but isopropanol, which is I'll teach you as an alcohol, if you have about 70% of this and water, about 30%, adds up to 100, yay. What do we call that mixture? We call that rubbing alcohol. Which you can buy at almost any local store, like a supermarket or big box store. And in the last 5 or 6 years, they've been making rubbing alcohol where the isopropanol is up to 90% and the water is only 10%. And in our daily life, with the pandemic, isopropyl alcohol, rubbing alcohol, or even pure isopropyl alcohol, you can rub it on your skin to do things, but it will disinfect things. Speaking about disinfecting, I remembered a story, and that's when I was a little kid, and even older too. When you go to the doctor's office, what's one of the first things they do? Take your temperature. And I'm doing the old way of putting a thermometer underneath your tongue. And you sit there for 3 minutes, and the nurse come in, take it out, and look at it. But if you watch back when I had the glass thermometers with mercury, now it's all digital with thermocouples, electronic measurements, but they'd have this sort of like a V-shaped glass container with a liquid in there, and they'd put the thermometer in there. When they're going to take yours, they'd take one, there'd be one in each room, examining room. They'd take it out, wipe off any liquid on there, put it under water, wipe it again, and stick it under here. What was in that V-shaped glass container? Rubbing alcohol. If they didn't wipe it off and rinse it, it tasted it. I remember that when I was a little kid. Oh no, wipe it off, please. And if the nurse was quick, she got it in your mouth before you figured out you didn't rinse it. But they'd wipe it off, and rubbing alcohol does kill germs and does kill many things that you don't want. And in fact, I've let's check something. We got time? Oh, we got time. I'll get you out of here before midnight. Scared you, huh? And regular alcohol, if you use isopropyl alcohol, anything 60 to 80%, which rubbing alcohol is, it will kill. Specifically, you'll find 70% alcohol available. Everybody see that on their screen right now? Yep. And it will kill it, isopropyl or ethanol, on a surface. And one of the things I did a year and a half ago when the pandemic really hit hard, you went to a local, the first thing I did was I went to my local big box store and I couldn't find rubbing alcohol. And I'm thinking, So I went over to Home Depot and they sell, not for putting on your skin, but for working. They had ethanol in cans. It's mainly for ethanol for certain type of alcohol burners. And I bought a gallon to have on hand to clean down surfaces because that was 100%. And it was, I just, for emergencies, I had that. Then I finally got some rubbing alcohol too. But that's the joys of being a chemist and knowing these things. All right, let's get back to solutions. That's not what I want to get back to. That's what I want to. Now, I'm going to turn the switch, click. Will this be on a test to the off position? When you form a solution, especially in water, and this is mainly because water is our most common thing we use in our daily life to make a solution. Say if you put salt in the water, forces are broken in the solute, such as sodium chloride, a solid, they're bonded together, and the water, for water, and ions are surrounded by the water molecules. What they meant here is that the forces holding the water together, hydrogen bonding, are also broken, and we call this hydration. And the switch is off. All right. If I had a dial that only went to 10, I just turned it to 1,000. This is probably one of the most useful things I'm going to teach you this semester. And you can use it the rest of your life in your daily life. Yeah, really. And you should know this. And that's the principle of like dissolves like. Everybody get the message? And like dissolves like, what does that mean? It means like solutes are soluble in like solvents. And what does that really mean? We have polar solutes are soluble in polar solvents, and nonpolar solutes are soluble in nonpolar solvents. When you mix a polar solute in a nonpolar solvent, it's not soluble. And vice versa. If you take a nonpolar solute and mix it in a polar solvent, it's not soluble. Like dissolves like is polar solutes are soluble in polar solvents, and nonpolar solutes are soluble in nonpolar solvents. And even on the slide I have, know this. Boy, you should. All right, what does this mean? Well, let's look at some important chemicals in our daily life. Now, things that are things that are polar. The most polar substance in our planet and the universe is water. Now, other things that are polar are most salts. Now, like dissolves like is a rule of thumb. I need to describe that. Like dissolves like is not a law. It's a rule of thumb. Oh, it's written on that thumb. Can't you see? Oh, that was an awful joke. Bad Dr. White. But anyways, it's a rule of thumb. What does a rule of thumb mean? It means it's true most of the time, like about 90, 95% of the time. There are times when it's not. A law is always true. So if you have something that's mostly true in chemistry, and I think in science too, but in chemistry, we call it a rule of thumb. I guess either one. And that's what like dissolves like is. It's not always true. Now, what are polar things? The most polar substance is water. Salts like sodium chloride, sodium fluoride, which is found in your toothpaste, and other salts, potassium bromide, those are calcium chloride, those are all polar. And another one, alcohols like ethanol or isopropyl alcohol are polar. Now, an example of something polar, which you don't know, but I do because it's technically an alcohol, not the kind that gets you inebriated, would be sugar. Sugar technically is an alcohol. It's also called a carbohydrate, but sugar is polar. Now, what's nonpolar? An example would be vegetable oil is nonpolar. Gasoline is nonpolar. Vaseline, also known as petroleum jelly, is nonpolar. And what else? Oh, baby oil is nonpolar. And what would be one more? Oh, let's do two, because we'll learn about this later. Dirt. Yes, dirt is nonpolar. And grease is nonpolar. And this concept, like dissolves like, I'll come back to later on because your soap uses this to get things clean, like your hands, or if you're washing dishes with dishwasher or dish washing soap, or if you're doing your laundry with laundry detergent, they all work on the principle like dissolves like. And I'll be teaching that. You should know water's polar, salts are polar. You should know at least vegetable oil, gasoline, Vaseline, and baby oil is polar, non-polar. And what does this mean? It means that if I mix water with salt or alcohol, that should be soluble. Now, a while ago, I had a Chem 1211 student who was, this was when we were face to face a couple years ago. I just taught this, I teach in that course too. And he said, are you sure about this? I said, yeah, it's a rule of thumb, but 95%, yeah, it's going to work. So I don't know about that. And I said, well, what would you want to do? And he said, well, if I take vegetable oil, will Vaseline be soluble in it? I said, good question. I've never done it. Next lab, I said, do you mind doing a demonstration for the class? I asked them in private because I don't like to put students in a position where they feel uncomfortable. And some people don't like getting up in front of a group. I do. I've been doing it most of my life now. I'm doing it right now in a way. I'm not getting in front of you, but anyways, he said, no, I'll do it. So next lab, I got some vegetable oil, some Vaseline, a beaker, and some spatulas. And he took some vegetable oil, put it in a beaker, put some Vaseline, mixed it up. Surprise ending. And lo and behold, it was soluble. We had a homogeneous solution or a solution. Now, why you'd want a mixture of vegetable oil and Vaseline, I don't know. You're not going to cook with it. You're not going to consider, but at least that's something to know. Like dissolves like. Now, have you ever gone to a gas station and after a rainstorm, you see some puddles and the sun comes out, and above the puddle, you see sort of like a film with the rainbow on top? Well, what happened is in gas stations, most people are sloppy with their gas pump. So there'll always be some gasoline spilled on the ground by the pumps. And if it rains, water is there and it interacts with the gasoline. Now, gasoline, let me get back to that slide, is nonpolar. Water is polar. Like dissolves like. Things that are polar are soluble in polar things. Things that are nonpolar are soluble in nonpolar things. Well, in that case, water is not soluble in gasoline, and gasoline is not soluble in water. And because of that, and also the density of gasoline is less than the density of water, you learned about that in our density lab. Hold on one second. Two more rings. One more ring. I like my ringtone on my Bluetooth phone. Stop. Thank you. Well, anyways, gasoline is less dense than water and floats on top. And the way the light interacts with that heterogeneous mixture, not a solution, causes the light to diffract and give all those colors. So next time you're in a gas station after a rainstorm and the sun comes out and you're with a friend, neighbor, loved one, and you see that nice, pretty rainbow on top of the water, on top of the puddles, you can say that's due to light dissolves light. And with that, I think this would be a good time. I'm going to end a couple minutes early because I don't want to get into the next part and rush and finish. We'll do that tomorrow because we're not going to do a problem set before a test. That's cruel, unusual punishment. And I don't do that. It's not being polite. And I try and always be polite. Remember, tonight, my office hour will be at 8 p.m., not 5 p.m. It's only for tonight, and I'll go an hour or so. And if you have any questions, show up. I'll be there to help you. Remember, use the office hours login. Tomorrow, we'll have our lab. Actually, I'll have to wait until next Monday for like dissolves light, but you can wait till then. Tomorrow, we'll have our lab. And then right after the lab, we will have the test. And with that, I'm going to say, Gangazoon, don't forget the lab that was due yesterday. You better get it in. You don't want 0 points. And I'll see you tomorrow morning. Bye now. Gangazoon. Be healthy.